It looks like we can start. Welcome back, everyone. Sorry for the interruption to class last time. Just felt like it wasn't a good day to infect people. I think a sneeze could have made it to the back row. I'm a little bit hopped up on pseudoephedrine, but I think we'll be able to get through the day. Any questions at all, folks, to start us out? Okay, well, last Thursday, we left off on exam right before the information right before example 4. So our goal today is to finish off these notes here in chapter 1. Shouldn't take us too much of the class. Then the remaining amount of time, we're going to make a start into chapter 2, most likely to be finished next Tuesday. So the due date here is reflected a week away from next Tuesday. And this due date is now finally official since we will finish chapter 1 today unless something catastrophic happens to the technology and we couldn't finish. Probably unlikely. But welcome back, everyone. And just a reminder for how things are working in this class, since it's only our third class meeting. If you're new to the class as well, some people have added the class before the last add drop date. Everything that happens on the Moodle website is pretty much a big document and form where you can research stuff. The syllabus will be posted here. If you can't make it to class, even if you're in the in-person section, you're welcome to join through the Zoom link here. And also, a lot of people will probably be checking out this link. This is where all the recorded lectures are going to end up for the course. Down below, we have the required software that we're going to be using. I said that in a kind of heavy way, not strictly required, but this is the major software platform that we're going to be supporting our studio. If you have any issues getting that installed, don't hesitate to reach out. They'll be happy to help. But again, a lot of these matters you can just take a look at on the first lectures, the first 3 lectures that are, or first 2 lectures that are given here in the class recordings. Aside from that, there's lots of ways to do this class. Some people are probably downloading the notes or printing them out. The blank notes are found here in a document, and everything that we do ends up in a chapter folder like this one. Clicking on it is going to show the solutions that we've worked out so far. So that's why there's blank lecture notes if you prefer a blank document, and also any required files that go along with the chapter. Then finally, after that, for the assignments, just click on the folder. We'll see some relative documents for filling out the assignment. There's really a pretty strong degree of parallelism between the lecture notes as well as the assignment problems. For example, exercise 1, just a new scenario of what we did on example 1 in the lecture notes. I'm going to try to mostly keep that kind of format. If you ever do an assignment though and you feel like we didn't do this problem at all, that's a great question to ask about in class or bring during office hours, something like that. Even through an email, I'd be very happy to help out. But for where we're at right now, in chapter 1, we were right at this location. We looked into doing some plots. If our data is categorical, we gave a bar plot. Now we're turning over to quantitative data, and the relevant plot there is a histogram. This is confusing in a way because the bar plot looks a lot like a histogram, but the histogram is special here. The idea of this histogram is we're dealing now with quantitative variable, and therefore there's a specific order to the data, which comes from the order of the real number line itself. So before we go too far on that, we should just draw out a histogram so we know what we're dealing with. So I'm going to provide one about right here. So let's give just a quick sketch of a typical histogram. So in this histogram, we have 2 axes that are typically plotted. Here we have the horizontal axis for x, the quantitative variable. So this variable could be anything like time, distances, heights, anything that has a unit that can go along with it. Going up this way Here, this is challenging. I have to write sideways. This is the frequency. And that is not quite how you spell that. Let me try again. And now finally, here's how the plot emerges. Let's say our plot goes from 0, 1, 2, 3 to 4. Next part, let's say from 0 to 1, we have a rectangle about this height. From 1 to 2, the next rectangle goes about up here. From 2 to 3, here to here. And 3 to 4, we have another rectangle going through this way. So essentially, we just have a whole bunch of rectangles describing our data. And have a second thought on that. Let me move frequency slightly more to the left this way. Next, on the horizontal axis, we might have something like, say, 0 to 1 to 2. And finally, what all this is telling us is, if we look at any specific rectangle in this histogram, say maybe this one, from 2 to 3, the height of this rectangle, you know, I might need some better values here. Let me try out again at 1, 2, 3. That would make a little bit more sense. Now, finally, the height of this rectangle, if we move over to the left, is at height 2. And then this tells us there are 2 observations between 2 and 3, possibly equal to the boundary points 2 and 3 as well, depending on how these are defined. So that's what we're meaning by the histogram. Between the 2 and 3, oh, let me fix that highlighter, is referring to this location here. And when we said there are 2 observations, that's just because the height of that rectangle was right at height 2. So that's the idea of dealing with the histogram. Again, they look a whole lot like a bar plot, but there is one critical difference. Let's scroll up to on the document just to look at our last bar plot. Well, I guess this is a good enough as one as well. We might say this bar plot has an interesting shape where there's a peak roughly in the middle. But, you know, that just depends on if you made winter come first. This did have a natural order because there's seasons, but you could have made summer come first and make the data look a little bit different. There's nothing stopping you in making that happen. Whereas down here, we're prevented on changing the rectangles in this histogram whatsoever, because like it mentions here, quantitative data inherits the ordering of the real number line, and that's this axis right here. It would never make sense to have a 3, 4 in this location and then go 0, 1, for example. So we have always a natural ordering. Because of that, when it comes to a histogram, we can describe the shape, but not when it comes to a bar plot. Let's actually make that part of our write-up here. I can highlight that table. Let's drop it over here. So when it comes to the bar plot, we do not describe its shape. And that's because, once again, you could rearrange the actual categories in a bar plot to show any shape you'd like. In fact, if this were just eye colors, not the seasons, then there's no ordering whatsoever between these values, and you could really give this any kind of shape. But the histogram, we do describe its shape. We will describe the shapes of histograms. And that's a worthy thing to do on its own for descriptive statistics, just to describe what the data looks like. But it's actually a deeper reason for this. We'll use the shape of the histograms we see to inform which statistical method we can actually use to treat the data. Some data is skewed so severely that the normal methods don't work, and we have to see when that happens by examining the data. So that's what a histogram is. Next thing we're going to do is describe shapes of histograms by mentioning any kind of deviations from the overall pattern. We will look at that. We'll consider that to be an outlier. That's kind of redundant right here as well. Need to look into those notes. We'll also describe the shape, the center, and the spread, and whether the histogram is symmetric, skewed right, positive or positively skewed, versus skewed left. So let's draw down some fresh histograms to get all those ideas in order. Starting with one that would look like skewed right. So if our histogram looks like this, I'm just going to kind of draw a generic one without units on the axes. Any histogram that has this kind of shape would be considered right skewed. What makes this one right skewed is it's all about where the data is trailing off. Skew to the right means the histogram extends much farther out on the right side, the right tail of it. Let me highlight that as well, than the left. And that's what we're looking at right here. The data trails off to the right versus the left, giving the right skew pattern. A lot of things that are right skewed could be, for example, survival times. Say, if you have 100 light bulbs, then you're describing how long they run until they burn out. That's usually a right skewed type of distribution. Or it could be something a little bit more morbid in, say, the sciences. We could have a collection of rats, a virus that we're analyzing, and we're looking at the survival time after injection. So all those would potentially have a huge right skewed shape. For left skewed, same idea, just imagine this thing is reflected. And this is what left skewed could look like. Let's go rectangles in this order in the histogram. Aside from being just left skewed, we could have some trailing out observations on the very far left. At this point, we might be looking at outliers right here. And in chapter 2, we'll give a test for, or rather a rule of thumb for when things are considered an outlier and when they're not. But what makes this set left skewed or skewed left is that the left side of now the histogram extends much further out than the right side. We're looking at these trailing observations. And now we have that left skewed pattern. Moreover, these could be considered suspected outliers. So there's many different ways to actually give a nice display of your quantitative data. The histogram is not the only option. We'll see other options in chapter 2. It's a great way to get started thinking about the data and the shape of the data it takes. Any questions at the moment, folks, with our 2 displays here? Okay, let's actually see if we can add some context to these, like we mentioned before. On this axis, this could be survival times, let's say, of something less morbid, of light bulbs. Light bulbs would have this kind of feature. Now for the left skew data, let's think of a context where that could fit. In my opinion, that's actually kind of harder, and it's sort of mysterious why. It seems like right skew data comes up a lot more often. The left skew data, you've got some time to work to actually find it. Any volunteers for a particular context where the data might look left skewed? I have one example, but it's like my go-to example. It's not that creative. Well, for my go-to example, here's one set of data that turns out to be left skewed. Left skewed often comes up if there's an upper bound that cuts off the data, as in no observation could potentially come up larger than whatever this value is. And that could be something like, say, percentage points. This could refer to 100% on, say, an exam. Lower end, let's say the lower end's clear out here, just to give a slightly warmer picture to all this. Let's say that right at this location, we're at 0%. Then exam data typically looks about like this. The data clumps up to the right, since there's no potential to go beyond 100%, unless some weird kind of extra credit is baked into it. The data only has the opportunity to trail off to the left. So we would get left skewed data in that kind of situation. Let's say that these are grades on a, let's say, organic chem exam. That would look about like that picture, I'd say, almost always. So that's the right skew data, the left skew data. The problem with our statistical methods is if our data is too skewed, contains too many influential outliers, we have to use other kinds of methods that are less powerful, give less stronger conclusions. So what we hope to see in our data is something that looks like this. Let's say that this discussion continues. And this is going to be our display for symmetric data. If our data is symmetric enough, then we can use a wide variety of statistical methods that have a lot of power, give very strong and broad conclusions. And this is about what symmetric data would look like. I'll put a main peak right here. And we're trying to put out a histogram that where if you fold about a dotted line through here, the heights of the rectangles in the histogram are going to be roughly mirrored on the left and the right. So this would be very, very symmetric data. Let's break it a little bit, since if your data is 100% perfectly symmetric, you might be suspecting it's fake data in the first place. Real world data is typically messy, never perfectly symmetric, unless by some miracle it looks that way. So let's put in more histograms or rectangles going this way. So now these data don't look perfect, but if you did some kind of study and you did get this data, this could be cause for celebration, especially if this was some kind of capstone project, because we would call this highly symmetric. Again, no data has perfect symmetry that's real data, except for some very rare cases. So even if it's highly symmetric, it has a slight skew in a specific direction. You wouldn't have to mention this if I'm asking if it's symmetric or skewed. You could just say highly symmetric, and that would qualify for this problem. But if you want to give more information, which direction is the skew? Is it left skewed or right skewed? That's slightly in the picture. Oh, sorry, I missed a few chats. Sorry, yes, absolutely, Hazel. Even if it has suspected outliers, we can describe it as left skewed. And you know what? A growing population could make sense for that. Again, sorry, folks, for missing the chat on that. I'm going to try a little bit harder to watch for the chat notification. And for these data right here, it looks like the slight skew on this, let me match my color coding, would be to the left, really just because of this one rectangle right here. So our data trails just barely off to the left. So let's say here, it's highly symmetric with a very slight left skew. Well, any questions, folks, about any of these displays here? Okay, so our hope is our data looks like this, but we're going to see some pretty messy data where we say our data is roughly symmetric, but we'll still consider it to be symmetric enough to use some pretty powerful statistical procedures. So the big takeaway here is, even though we're often looking for perfect symmetry when we're asking, is our data symmetric? We are very forgiving with deviations from symmetry when it comes to declaring something symmetric. It's when it starts to look like this, where the main peak is so far to the left or so far to the right that there's no way we can call it symmetric at all. Those are the problematic data sets we'll worry about more. But continuing on, we should produce our own histogram. We're nearly done with this chapter where our main goal is just to look at data types and produce graphics. And so here's our final problem of the set. We looked at this problem before on the first parts of the class, but now our goal is to take a look at this closer by handling the FEV variable. But note, that's just one variable, this data set. This has a lot of relationships amongst the various variables. So to really give a better graphical analysis of this, we need some of the techniques we'll see in chapter 2. So we'll come back to this problem right here to see what's going on further. But for the reminder and the rundown of this problem, FEV stands for the forced expiratory volume. So this can be done in a medical setting if you have pneumonia and they're wondering about your lung function. You take a big, deeper breath, they say full inspiration of air, and measure the volume of air that you, let's see, how they say this, that you can forcibly blow into some kind of device. So that measures your FEV in liters. And in this data set, we have loads of children in this data set where the FEV has been measured, as well as height and sex. 0 was the coding variable for female, 1 is for male. And the smoking variable here is whether the child was smoking or exposed to secondhand smoking, I'm assuming, in this data. There's lots of zeros, but there are ones here to say the child was smoking. So there's probably a big relationship between FEV and whether the children smoke or not, but we'll see what that looks like when we get back into chapter 2. For the moment, here's what we want, a histogram of the FEV variable. So for that kind of operation, we'd be going into RStudio. So recall, you download this just to get the base programming language R going. But then we use this so-called integrated development environment, IDE, RStudio, that makes a program just a lot more easier to use. So that's this pulled up right here. To get a histogram going, the first thing you want to do is import the data. That's a really large data set, so there's no way we want to type these out by hand. So go to this tool right here, import data set. To me, this is the biggest quality of life feature of RStudio because importing data sets by hand, by pointing your files to the right directory, is a real pain in R. Once you click on this, you automatically want the first option. So my files I'm going to share are going to be made in a way that it's ultra compatible and very intuitive to import into RStudio. So click on that. And now you'll have a file picker. So we're trying to go to wherever you saved that file. Back to the Moodle website. It's all inside right here in chapter 1, any files that we're going to use. So download FEV to the file that makes sense. I have it on a thumb drive. And so back over here, what I would do is go to my thumb drive location. Here it is, chapter 1, and just double click on FEV or click open. Then you get kind of a scary window, but we're on the right track. This is where we need to be. This is a data set named as FEV, and we can let that stand just as it is. If you like, you can change this to something like example 4. That'd be totally fine if you prefer. I'll leave it the way it is. There's a whole bunch of options right here, but everything is really all ready to go on the files that I'm sharing, as long as you see everything here in bold. So these are the variables that we're recording, and I'm pretty sure every file that I share is just automatically set up so that all you have to do is click on import. If that's ever a problem, let me know right away, and I'll look into what's causing the trouble. After you do that, this is what happens to RStudio. The script area gets really busy. They're showing you the data frame that we just imported. I usually click this off since there's really nothing to do here. This is just descriptive information. So we'll put some information here as we construct the histogram. And Hay said, I did the same thing, but it's not bold. Let me see if I can reset and walk through it again with you. So to reset everything in here, to try it again, you want this little broom icon. Pretty cleverly described icon. It just sweeps out everything. So click on that, and then everything is gone from the environment. So let me try it again and let me know if this helps out. So click import data set from text. Pick the file we need, 3350 is where I've got it. And this is what it looks like from my screen. So instead of the values in bold, do you have something like V1, V2, V3 in that location, Hayes? Or is it looking more about like this? It is the same? Oh, gotcha. That might be just an operating system issue. So maybe the bold is not as important, but what it should say is the actual variable names. So if that's the case, you should be all set. Awesome. Yeah, I think that must be an operating system kind of issue. Who knows? This is machine I'm using right here is Windows 10. Probably in another 5 years, we might update to Windows 11. But after it's all imported, let me click this off. I usually pay more attention to what happened right here. So this is the data frame. Click on this little play button and it expands all your variables out. We want a histogram of the FEV variable, this one right here. You know, those dollar signs are pretty weird, but they serve a big purpose. So let's give this a try. First, if you knew nothing about RStudio and you want a histogram, you should just start typing slowly. Histogram is HIST, and there it is. The histogram function pops out that says this is the generic function hist computes a histogram. So we can either complete the typing, put in the letter T. I usually press enter just to auto-complete the syntax, and you'll get this here. Now, my next step isn't going to work, but this is a good step to take anyways, just to see what goes wrong, why it doesn't work. It's a common mistake going for a histogram when you're dealing with a large data frame. I think a lot of people would just want to go FEV, but you might tell it's problematic, right? Because FEV contains 5 variables. RStudio has no idea what you're talking about if you just say histogram of the FEV data frame. But let's run it anyways. Hit Control A, highlighting everything, hit Control Enter, and it says, well, X, the value that should go here, must be numeric. We have numeric stuff here, but we need that one variable. $FEV is basically the hint on how it works. So type in a $. I guess the reason it's a $sign is we're selecting one variable out of the data frame. And notice the moment you type in a $, you have this little tab. You could just type in age. But this is actually really important sometimes when the variable description is complex, because you have to type that in verbatim, case, syntax, spacing, and all. So oftentimes this is a foolproof way to make sure we don't get any weird errors accessing the FEV variable. So I would just scroll to this one, hit enter, and this would do it. This is far easier to do than the bar plot they were doing earlier, so that's kind of weird. The histogram function is just much easier to work with. Now to run this, either do the Control A, Control Enter, or if you're rather point and click, just as valid, highlight all of your syntax and click on the Run button, this one right here by the red dot. And we've got something, folks. That's a histogram. Lots of things we can complain about on this histogram, though. First of all, the scale looks a little bit weird, but we can fix that just by resizing the windows. Other problems here are that main title just looks strange. Even worse, that's supposed to be the unit for the horizontal axis. So we need to fix several things. And what could offend people even more is the extent of the data, the extent of the axis doesn't even go as far as the extent of the data. Ours doesn't always plot these perfectly. Let's fix these things one at a time. Starting with the main title here, you could fix that and just say main equals. Now you're influencing the main title. And I'll leave this up to you. You can come up with a main title that says the histogram of the FEV variable. That'd be very descriptive. But for me, that feels redundant because we know we're dealing with a histogram. And down below, when we give the unit, we'll know what variable we're dealing with. So I'm a bit of a minimalist when it comes to this, but you don't have to copy me. You're always allowed to put in whatever main title you prefer. But as a minimalist, this is what I would do. I set main equals to quotes, and then I ended the quote. That has the effect of just deleting everything here. So hit Control A, Control Enter, and then that's fixed. We shouldn't leave it as is. If it's a weird title, it should be descriptive and accurate, or just kill it all outright, and that's fine as well. Next thing I would probably do to this is fix that right there. That's more important. We need to say what the horizontal axis represents so that people can actually read this plot and understand it. So that's the x-axis label. We start by writing, just like with the bar plot function, xlab for the x label. Oh, sorry, missed a couple chats there. Summer says, I don't have anything show up in the plots box. Oh, glad you got to show. One thing that can happen though is, let me demonstrate. If your windows are really, really short, sort of like this, then the whole thing could just kind of blow up and not show. So sometimes that's one reason why a plot might not show up. But thanks for mentioning that. I've seen some other weird issues that do come up. So let me know if any other interesting errors ever occur. I'll be happy to work with you on fixing those. So next for the X label, we'll set that equal to, just like with what we did on the main title, we're giving this a string when we pass it to this parameter. So start with the quotes. And here, this is FEV measured. Let's say, instead of making it too long, I'm going to write FEV parentheses in liters. I don't have any specific advice for this other than it should be descriptive about the variable. It should mention the unit. And you don't want to make it too long or else it could have some problem with the graphics. But aside from that, anything descriptive here will do just fine. Closing the parentheses now seals off the whole histogram function. The frequency right here is actually just fine. It's descriptive. It's nothing that we need to change. So hit Control A, Control Enter, and I got like 3 different warnings. And I noticed I misspelled liters. I don't think that's what the warning is. Display list redraw incomplete, dot tray catch. Sometimes these are things you might want to Google to figure out what they're trying to express here. But let me go one step at a time. That should be liters this way. Let me run this again. Okay, looks like no other errors. I'm not too sure what that was. Could have been when I squished the windows tight and it couldn't display. Not too sure. But from here, if this is your histogram, I would say it's totally fine. I'm okay with any main title, but it shouldn't be something weird that doesn't make sense, some strange syntax. If the extent here doesn't look too great, you can fix it, but this would be considered for full credit. But let's do a little bit more just to touch it up. Let's see here. The height of this looks like it's okay with a height of 150 by my eye, but this is the major offender. Let's make the extent of the horizontal axis go from 0 to 6. That looks more appropriate. So go comma, drop a line, and just like if you're affecting the vertical axis, you'd be using Y limits. Here we just use X lim. So this is the extent of the values on the horizontal axis. And Summer says, Control A and Enter doesn't work for the plots for some reason. Oh, strange. Could be an operating system quirk. And I believe Summer is using Linux distribution, if I'm correct. And so you have to click on Run, and then it showed. So you're saying for your distribution, go like here and click Run this way to make it come up? Okay, well, for the X limits next, for here, we're going to go C. Oh, that's in the chat. We're going to go C to combine. We want to start out at 0 and go up to 6 or 7. Let's make it be a 6. That makes more sense, I would say. And this would fix our horizontal axis. One last parenthesis to close the last delimiter. Another cool thing about RStudio is when you close a parenthesis or delimiter, it shows you the associated parenthesis that was open. So look to here. If that doesn't get highlighted when you close your final parenthesis, we have mismatched delimiters. There's too many opened or too many closed parentheses. So that highlighting up there says that matched up with that one as intended. So now let me try the method of just highlight it all. Click Run. Now our data sits within the axis. That looks a little bit better. And if you still want to touch it up a little bit more, click on Export. Now down to Copy to Clipboard. And from here you can type in, the pixel width and height, but I usually just drag things around. Mainly what I wanted to fix is the numbers here showing up a little bit better. So I felt like it looks awkward when one of those tick marks is skipped. I'm not too super picky on your plots. So major thing I'm looking for is the correct description here. And if you go with the main title, it should be something that makes sense as well. So that's our plot. Either click the copy plot button here or use the snipping tool on your operating system. On Windows, it's Windows key Shift and S. Darkens out your screen and you can just highlight in this kind of way. Then back to the document, hit Control V, and we've got our histogram. But that's just a way to do it. Again, let's show it a different way for folks who do prefer. Here, you could just click Copy Plot, come back in, and it didn't work that time. That's weird. Let me try one more time. Copy to clipboard, copy plot. Doesn't seem to work on this one. That is so weird. It worked last class for the bar plot. So something weird with my system here. Let me know if you're having the same kind of issues. I believe folks said it worked for them last time they tried. If you're having the same issues as me, click on the export, copy to clipboard, and again, just a normal snipping tool will work. In fact, you can just hit print screen. Let's see, where is that on this keyboard? That'd be function and the key above delete. But that's really heavy-handed because if you go the print screen route, you've got too much information, really. We just wanted that part there. So back here, using the snipping tool, that's finally our graphics for the FEV variable. Any questions at all, folks, on producing those graphics? Okay, so in producing this, we see that, well, we took a look at all the FEV data. Here's how it aggregates. What we want to know next is the shape, center, and spread of the distribution of this variable. So let's work on that next. For shape, we could say a whole lot of things, but the major thing that I'm looking for whenever the shape question is asked on a histogram is whether it's symmetric enough to call it symmetric or if it's skewed. If it's symmetric, you'd want to go to the major main peak. Imagine folding the paper along this line. Symmetric would mean that the rectangles on the left would roughly overlap with the rectangles on the right. But all of these rectangles look like they would have no match when we folded over the page. So I probably wouldn't call these symmetric. I would say at least very, very roughly symmetric is what you might say to these. This definitely has a skew going on towards it. So which direction would you folks say the skew should be for these data? I agree. This ought to be data that is skewed right. And Hayes asks, why is there 2 blocks between 5 and 6? So these 2 blocks means there are some people in this data set that have an FEV in the 5-liter range and maybe all the way up to the 6-liter range. So those is what those 2 observations are saying. Let's write that out here. Oh, that didn't work. Let me try again. So this tells us there are observations with FEV values between 5 and 6. So that's what those 2 blocks way down here are representing. They're way, way low in height, which means there's a very small frequency of those observations. This rectangle between 2 and it looks like 2.5 tells us about 150 children have FEV value in this range, 2 liters to about 2.5 liters. And as far as the shape distribution went, I think folks said right skewed. We'll say here, these data are right skewed. And we might say here, very roughly symmetric. So we've got right skew data we're looking at. That's what we're mentioning when we say the shape here. The next 2 steps, I have to admit to you, feels really uncomfortable with what we're about to do, because this is really a topic that fits better into chapter 2. But think of what we're doing when we describe the center and spread. We're just inching towards our objectives in chapter 2. When we say center, we're talking about a number between 0 and 6 that does its best to summarize all of the data that you see here, the most typical observation. It's where the data is clumping at the most. We call that the center of the data. But what we're doing here is we're describing it purely qualitatively. We're just eyeballing it, in other words. Later on, we're going to make RStudio do the work for us and just calculate it. Calculate the sample mean, the sample standard deviation. But here, we're going to do this uncomfortable task of saying the center is approximately, and I'll leave this up to the class. It's open-ended in the sense that a lot of observations will, or excuse me, a lot of responses will get full credit if they're in the right ballpark. If they're too far away, then we could lose credit. For example, the center is not at 0. There's not even any data there. The center is nowhere in 5 and 6 because there's hardly any data there. The center is going to be where the data clumps. Any volunteers to say about where that would be as one number? Yeah.
About 2.4.
I agree with you. Right around here, it seems like all the data just spreads out right around that location. So that's going to be our center. It's approximately 2.4 liters. So right here, we have the center. Let's make RStudio compute this and see how close we were. This is a preview to what we're going to do in chapter 4, so you don't have to worry too much about this, the syntax on this step. But the syntax really isn't too bad either. All you have to do is say, drop a line and go mean of the FEV, not the whole data frame. We use $sign to select strictly the FEV variable. So if we run just this, let me do the highlight and click method. It says the mean of all of the FEV observations was 2.6 liters. And that's kind of the cool thing about doing this just by eyeballing it. We are really, really close on saying 2.4 liters. But you know what's also kind of interesting? The 2.4 liters actually is probably the better value. The reason the mean is 2.6 liters is because we are skewed to the right on these data set. It took the sample mean and pulled it to the right at the same time. It's making the sample mean not a great measure of the center. So what we pick out visually really looks like more the median, the 50th percentile of the data set. But let's go on to the next one, the spread, and go from there. Any questions so far, folks, with either of these values? Okay, for the spread of the data, if we were in chapter 2, we'd be using either the standard deviation, possibly the interquartile range for highly skewed data. But for us, if we're doing it qualitatively, it's a little bit tricky to describe the spread. Here's one way to do it. We will use the range. Let's make a sentence out of this to connect our thoughts. The spread can be described by the range in chapter 1. I'm saying range in chapter 1 just to emphasize this might be the only time we use the range to describe the spread of the data. It's the only tool we've got, so that's why we're using it right here and now. The range is going to be equal to the max minus the minimum value, which is kind of weird in a certain sense. One way to describe the spread of the data is just to say it goes from about 0.5 liters up to 6 liters, but I gave you 2 sets of numbers. Oftentimes when people are describing the spread as a range, we're giving one number. We just want to know the length of the interval that contains all the data. That's more similar to the standard deviation and the interquartile range. It just feels weird when we do it the first time. And I don't know the exact max values or the exact min value, so I'm just going to say it's approximately, because again, we're just doing this qualitatively in chapter 1, about 6 liters minus, way out over here, looks like about 0.5 liters. which will give us 5.5 liters. So that's not where the data lives, but that's roughly the width of the interval that contains the data going this way. So from here to here, we can say range equals, well, approximately equals 5.5 liters. And that's how we're describing the spread in these data. Well, any questions at all, folks, thinking about the quantitative data, graphics, or the descriptions below? Okay, let me save this up. Oh, I saved a little bit early. One of the things I want to get in the habit of, and that I sometimes forget on these things, is any kind of graphic that we use, or anytime we use RStudio for something as put down here in our results, I always want to put down something that looks like that right there. Anything that's getting boxed out most of the time, except for the central limit theorem, that's the only exception. Anything that gets boxed out like this is just going to be syntax to help you to produce the graphics as you're seeing on the notes. And so the syntax for us on the histogram, I'll put down below right here at the end of the problem. I'm going to skip the mean thing right here because we're going to come back to that once we're in the next chapter. So let me just attempt to move my windows back. And again, if you ever notice that this stuff is missing on the write-up, it's probably because I just forgot. And I'll get back to it right away. Just let me know by email, something like that, and that'll be extremely helpful. Okay, so that's how we got the histogram to go through. Well, let's save these notes up. Chapter 1 is done. We're going pretty slow in chapter 1, a little bit slower in chapter 2, mainly just for the sake of absorbing this RStudio stuff slowly before we jump into chapter 11. So back to the Moodle website, just to pause for a moment and reconvene. We're now in chapter 2. Here we'll describe quantitative distributions with numbers. We're going to go from chapter 2 into chapter 11, working with a normal distribution when we come back next Tuesday. So think of chapter 1, chapter 2 as this is really kind of the introduction to the course, introduction to RStudio, and because there is no statistical class prerequisites to this class, we're trying to get through some of the earlier topics if you never took statistical reasoning or any other statistical class. So now back in chapter 2. The document starts off in kind of an unfriendly way, just a wall of text and formulas. But this is just the notation and some of the formulas that we're going to be looking at. These formulas are implemented very rapidly through RStudio. In fact, that whole formula highlighted right there, we used once when we calculated mean of FEV. All we were doing is implementing that equation there. So let's go for the top, absorb the context, and see which problems we can solve on this set. First, for the common notation we're going to use this class, if we just write down x and x alone, we're talking about a variable. If we know what variable we're dealing with, that x could be replaced with FEV, for example, or height or age, something like that. But generically, x alone is referring to a variable. We saw in chapter 1, n is always going to refer to the sample size. So how many observations we have in our data set. So that means if n is the sample size, x1 will be the first observation through x2, ... just as we keep on going until we get to the last observation, which must be described as xn because we have n pieces of data. So that's our sample. When we describe the sample's mean, we use y bar. Some texts use y bar. And they have very good reasons for using y bar in other textbooks. Our textbook went with x bar, so we're going to stick with that just to make the reading compatible. But if you've seen y bar used a lot, we're not doing anything different, just a change of notation. S is a little bit more standard. We'll always refer to the sample's standard deviation. And here's how we calculate out these kind of things. First, any questions, folks, on the notation? Okay. Well, we talked about averages on day one. Really, the very first problem on the notes, we had average values we were looking at and sample standard deviation values. It's synonymous with just saying sample average, like we mentioned. So if you decide to use this word, no harm done. I'll often say sample mean. All we do is we take the sum of the observations in the sample, x1 through xn. In other words, we just add them up. Different way to repeat that addition is just in the sigma notation here. Excuse me, summation notation. And then we divide by the sample size. But the sample size is once again just n in this problem. And so it goes into this kind of format. But because we're using RStudio, we'll probably never do this by hand unless you just really wanted to and you're bored. In RStudio, or let me just say it this way, using R, we say mean x, wherever x is, to get the same exact result. So that's how the function is implemented, kind of nice in a way, just fast and straightforward using the words you expect to be used. After we have the mean, this represents the center of our data set. So it's the typical value. If you had to take your entire set of data and use one number to describe it, the mean is probably the best way to describe your data set. But the center of the data is never the full story. We also have to know how spread out it is. And that gets a little bit more complicated. We do this operation. It says down here, the variance S squared represents the sum of squared deviations from the mean. Let's take a look at what it's doing really. If x bar is the sample mean, and you want to calculate variance S squared, we go to every single observation, find out how far x1 is away from its center, square that. Major reason for squaring these is without the power 2, the numerator sums to 0 for every single data set, so that's inconvenient. We need a power 2. Go to the next observation, square that, and so on and so forth down the line until you get to the last observation in the sample. So all of these values in the parentheses are the data's deviation from the mean, how far away the data is. So already we're describing how spread out it is. We square them so the numerator doesn't come out as 0. Then finally, add up all the summations of these deviations. It ends up here, and divide by sample size minus 1. And now you have variance. Kind of a nice formula. There's some oddities down here. Let me know if you're curious about what's going on here with n minus 1. It just seems odd to go from sample size n to sample size n minus 1. There's a couple ways to describe this. I think the most clear way is it's about degrees of freedom in the data. In other words, if I lost x2, maybe our data is written down on paper and I just lost it. Nobody knows what x2 was, but somebody calculated the mean and we know that value. Even if x2 is missing, we can still calculate s squared, the variance. You could solve for x2 if you know all of their observations and the sample mean. That's kind of a nice little concept there. It's in that way that the variance only is dependent upon n minus 1 pieces of information. So we use that down there when we calculate it. That's the hand wavy kind of expression. The more complicated answer is this estimator is unbiased if and only if you divide by n minus 1. If you divide by n, this thing is trying to estimate the variance of the population, and it will always underestimate. It's unbiased unless you put in n minus 1 there. That's equally weird, and if it seems kind of cool to you how these things are happening, a good probability course goes into great detail on those kinds of issues. But our objective is to work with the tools we have. We're not going to delve into the proofs of how, or derivations on how this came to be. More just get familiar with working with it. The weird thing about this is we don't actually typically use the variance in this course. The trouble with the variance is if our data has unit of, say, inches, the sample mean will be in inches, but the variance is in inches squared. It doesn't do a great job of describing the spread in the sense that it's a tremendous unit mismatch in the first place. We correct that by going to the standard deviation. It's literally just the square root of the variance, so that's kind of cool in a way. Whatever this was just goes down over here and we square root it. Now the unit for x bar is the same unit for S. And so when we're describing the spread and say it's this many inches, it makes a lot more sense than if you said this many inches squared, a unit mismatch. So if we're using the standard deviation, that's one we should describe for the R syntax. In R, all you have to do is say SD for standard deviation, X, and it implements this equation through this equation as well. So it does a whole lot of stuff. Well, those are the introduction to the statistics that we're actually going to be using. It's kind of weird to talk about them in chapter 1, but define them in chapter 2. But I think it makes sense because everyone has a pretty good intuitive feel for what a mean is, or average in the first place. But we should actually calculate this stuff, and that's the purpose of example 1. Last takeaway points is that it's not always easy to say how the standard deviation describes the spread. The range is easy. It's just the maximum minus the minimum, and that's how spread out your data is. But this quantity, when you go to calculate it, S, if your data is symmetric enough and mound-shaped, approximately 95% of all your observations will be within 2 standard deviations of your sample mean. So it's in that way, S is describing how spread out your data is. And we'll look into this idea a lot more closely in chapter 11, where it gets rolled into the empirical rule, or the so-called 68, 95, 99.7 rule. So that's our rundown that really can't skip this stuff because once again, statistics isn't even a prerequisite to this class, even though it's 300 level. It's kind of an awkward position to be in. Just means we go a little bit slower on weeks 1 and 2. Any questions whatsoever, folks, on the discussions here? Okay, let's put all this to practice on example 1. Because we were looking at a wall of text, I felt like example 1 shouldn't have context. Here, we're just strictly practicing those 2 functions, mean, standard deviation. So it has units, but there's no context. Who knows what this is? This is a negative as well. So it could just be some displacement from a starting position. We want the sample mean, sample standard deviation. We want to indicate these with the correct symbol and use the correct units as well. That's mainly to tie together the concept that these have the same units. I'm usually not too picky on units on actual homework problems. To make all this happen, we just go to RStudio and start putting in the data. This is a scenario where I don't have a file for these values, so we're just going to do by hand data import. First thing I would do is hit Control A here, and now just delete. We're done with that script. If I'm doing a new problem, I get in the habit of always clearing the environment. So go here, click that tool, and it wipes everything out. And now to import the data you see here to the right, I'll just call this X because I have no context of what it could be. Say equals, or use a left arrow. C is going to combine all the observations into one vector. And now just type them step by step, comma separated. So 5, 13, negative 12, 7, and 2. That gets us all our data. And it's not a bad idea to just run this for each new line you put in. If you're worried about making small syntax errors, for me, I could forget a comma or something weird like that. So hit Control A, Control Enter, and this is what you should see on the right. X is now stored as numeric data. 1 by 5 tells us we have a vector that is 1 column, 5 rows, and these are the data values to the right. After we have that, to get the sample mean, again, it's really pretty fast. Just follow your nose on RStudio and you're probably on the right track. Type out mean, throw X in there, go drop it down a line just to say this is our data and computations down below. For this value, standard deviation, go SD, throw an X, and this syntax should do the job for us. All right, let me run this and see what we get. Now let me know if it does anything weird on your end. So I'll hit Control A and then the run button. It gave us a mean of 3, standard deviation of 9.3. I didn't say what to round to on these, so use your best judgment and you'll be just fine if there's no indication on rounding. You don't necessarily have to copy in that whole number. That'd be kind of strange. But this is at the part of the course where you really have a lot of options on how you do this on your homework assignment. Imagine this is a real problem on assignment number 2. You have similar problems. If I was going to write down the options or the report on this, my options would be to do something like this. Here's option 1. If you're using digital tools like I am here, or if you printed out the homework assignment and you're just doing it by hand, you just want to go like this for the sample mean. X bar came out as, let me grab the value, 3 inches. For the standard deviation, it says use the correct symbol for each, so I need to use S now. Standard deviation, let's round to 9.3. That seems to make the most sense. Inches, and then that would qualify for a totally fine answer on that. Well, if you're typing things out, then that's another option to give your results in a homework set. So here's option 2. So in option 2, I would just be typing this all out. Let me see if I can actually get to that spot. There we go. There's lots of ways to type these things out. If you type out X bar, I usually put these in lowercase, it looks better, but if you type out X bar, that is really okay with me. You don't have to know any fancy typesetting in Microsoft Word or whatever word processing program you're using. X bar equals 3 inches is totally fine with me. Then S equals 9.3 inches finishes it off. In fact, this is very common. We write the symbol X bar this way, and if you type it out this way, just about everybody is going to know what you meant if they took a statistics class. So that's option 2, just as valid. For option 3, this is only for people that would like to do so. So in option 3, Microsoft actually has a pretty decently powerful equation editor. The way you access it on this computer, at least, is I have to hit the Alt and then the plus key. So my fingers go here, Alt plus. It pulls off this equation editor thing right here. But let me hit first, just to describe. Press Alt and plus. This is on a Windows machine, so if you're using other platforms and you're curious how that could go, let me know, and I could look it up for you as well. Inside the equation field, type X, then that slash, that was the wrong one, that slash there. I actually looked this up, but I forgot. Anyone happen to know if that's a forward or backward slash? Actually, I think that's the wrong one. Let me try again. Should be that one right there. Then just go BAR, just write it out. Hit enter once, produces the bar. Hit enter again, it centers the bar over your symbol. And then you can write X bar gets, or equals 3 inches. I want to emphasize, you totally don't have to do this, but if you are anticipating you're going to be using a lot of these kinds of things in your work, you're possibly maybe going to have to write out reports where symbols get involved. You can put in essentially any symbol. Mu is in there, sigma is in there, for example. All sorts of stuff can be typed into this, and so it's a decent thing to look into if you feel like you are probably going to use it a lot in your program. If I was going to put in S, I would just type that in normally, just S equals 9.3 inches. And that does the job. So either way you decide to do it is totally fine with me. And the last one I didn't put down here is option 4. Writing out the results using pen or pencil and paper works just fine as well. If you went option 4, you're probably thinking working this class like an ordinary math class. And again, that works just fine. You'd still have to give me your graphics, like these kinds of things. My margins are too large. Well, the graphics that we had right here, but you could always just take that screenshot of this and just email it directly to me, or print them out and just staple it to the last page of your written out work, and that works just fine. And I'd say just pick out whatever makes sense to you and stick with it, and you'll be totally fine in this class. As far as handing in homework, if you go this route, you just want to either scan, take a cell phone picture, and just directly email it to me, or hand in a physical hard copy in class, and that would work out as well. Well, any last questions at all, folks, on this example one? Okay, meant to be a pretty fast example. It was mostly a discussion on just writing up your results in a report once you're doing your homework assignments. This one is a little bit more exciting because now we have some context, some actual data that we're looking at, some bigger data. Context on this goes like this. It says, a veterinary anatomist, that sounds like a pretty cool job, investigated the spatial arrangement of the nerve cells in the intestine of a pony. So something could be off about that pony, could be sick for some reason, but we're looking into it. Here's what the anatomist does. So he removed a block of tissue from the intestinal wall. So imagine you have a cube of pony intestines. He took that cube of meat and cut it into many equal sections. So imagine now we have slides of that one section that was removed, lots of cross sections, maybe under slides to be put in a microscope. Counted the number of nerve cells in each of the 23 randomly selected sections. These are the number of nerve cells in those sections, and there's 23 pieces of data here. You can imagine this was probably done by the graduate students. Usually that's what happens in these kinds of labs. This is a lot of work, but this is what they produced. So from one section of the intestine, these are the slices and the number of nerve cells per slice. To better understand this data, we can't just eyeball it. I mean, we could to some degree. We know that the data tells us to expect between maybe 12 and 40 nerve cells, but we can't really see what the typical observations are unless we work out this a little bit harder. We want a histogram as well, because we also have a problem with our data. If it's too skewed, the sample mean does a terrible job of describing the center, and the standard deviation then does even a worse job of describing the spread. So the histogram is going to give us an indication of, is our data symmetric enough to really use these statistics in the first place? So let's begin by going into RStudio, importing all the data. So we're back over here. We're still learning this import function, so I'll go slow for the first few times we do this. But really the first thing I'd want to do is delete everything right here. Delete everything in the environment. You can either use the broom icon as before. There's another weird way to do this. You can say rm list equals. Oh, you know what? I think I actually forgot how that worked. I'm gonna have to look into that again. I'm gonna come back to you on that shortcut. Let me remind myself to actually do that. Relearn the clear environment shortcut. But again, that's just for folks that would rather type it down here to clear their environment. You can do it just as well by clicking the broom icon here. It wipes out everything, and that's just more for safety, since we could have potentially have a variable that we stored, which could conflict with what we're about to do in really larger problems. But the next thing we're going to do is we need to grab this data here. Go to import data set from text base. If you don't have the data file, it's sitting right inside here in chapter 2 on Moodle, example 2. So for me, it's on the thumb drive, like we mentioned before. Double click on this, and you should see number of nerve cells right here. I need to scroll down since my environment is kind of minimalized. If everything looks about like this, then just click on import, and your environment should turn into this. You should see number of nerve cells. This is the window I usually click off. expand this, and it should say we have integer values in 23 observations. Now, they told us our sample size was 23, so that's good consistency to look for after you import the data set. All we need is a new histogram, so let's get started on that. Any questions so far, folks, to the data import side? Okay, so a great function, just go hist for histogram. My data frame is example2. You could rename this to something more convenient rather than just leaving a default if you prefer. Let me type it in carefully by just putting in a few letters and then clicking or hitting enter on the right option. Again, everything here is important. If I forget the underscore here, I'm not going to have the right thing. We need to access the number of nerve cells. So type in the dollar symbol, and here's a good case where you just want to hit enter. I would never want to type in all that stuff. Doing it that way just guarantees we have everything imported in the way we want it. Next thing I'll do is write xlab for the X label and just describe this as number of nerve cells. So that's probably how I would do it. Notice I didn't do anything to the main title right here, which means it looks horrendous. We should never send out graphics that look like that for the main title. It should either be deleted or just made into a more reasonable description. My call is always to delete them, but that's just because I'm a minimalist. Let's actually put in a main title. So if you prefer the title for your histogram, go main equals, put in some quotes because we're giving a string to this parameter, and just come up with something. Any volunteers for a good main title for this histogram? I think I almost heard someone in Zoom. Kind of hard to come up with, right? If you're not sure what to put in the main title again, everything is kind of in context. You could just delete it. But let's go like this. Histogram of nerve cells in a pony intestine wall. Quite the description there. Let me expand this out so we can fit it better. So I guess that's an okay title. Let's run this. That makes more sense. If you go with the title here, it shouldn't have any crazy symbols. It should be descriptive. The reader should know exactly what's going on, and that would qualify. So let me extend this up a little bit more just to resize it. Either take a screenshot here, or let me try this again. Click export. Copy to clipboard is usually what I do. Let me try save as image, just see if I get better. You know, that just did the same sort of thing. You can now save this as a file, I suppose. What happened there? Let me try pasting it in. Nope, that wasn't the thing I was expecting. Well, let me try my normal thing. I usually click on export, copy to clipboard, copy plot. I saw something extra there. You have either a bitmap or a meta file. I'm not sure if that makes a difference on my end. Let me see if that fixed my issue I have having here. So as a meta file, hey, that actually worked for the first time this class. Really weird, it worked last class, but not this time. Let me go through those steps again if you prefer to go through that route. So either take a screenshot here, or here's the steps that seem to work today on this installation. Go to export, copy to clipboard. For reasons I'm not too sure of, Metafile seems to work today over bitmap. Okay, copy plot here when you're deciding the size of this is about what you'd like. Then back in the document, hit paste and you're on your way. We have a good distribution then. Here's the histogram for the nerve cells and that pony. Other thing I mentioned before is you can leave it this size, but they're usually going to take up a lot of page space. If you resize it aggressively, that's absolutely okay with me. I'll be able to read it as well. So we have the histogram. We want to describe the shape of this thing, and looking at this shape, hard to say what the direction would be for skew. Would you all agree that it's tough to determine skew on this one? It does have a direction on skew, but it's so minimal as to be almost non-existent. I would say for this, the shape is highly symmetric. But for highly symmetric data, when we go to describe the spread, excuse me, the center and the spread, we would just be using the typical functions. So for these highly symmetric data, let's put in mean, type in example 2 slowly, then $ highlight, number of nerve cell, type in SD for standard deviation, and do the same. Then we'll get some values down here on the console. We'll put them down in the report and be on our way. But I'm looking at the clock here. We're out of time. Sorry about that, folks. We'll come back to this next class, finish out the report, and discuss this syntax further. I'd hate to try to rush this and get it down on the report, though. But we did get this part in. So I'll leave the syntax for later. We'll have to come back to this problem here. That's one of the things that's kind of rough about some of these problems is they take a little bit of time to get through. Sometimes they get broken in half. I'm going to try to avoid that and try to end on a problem and not half start one like we did today here. But any last questions at all, folks, before we call it a day? Okay, well, have a great night, folks, and a great weekend. If any questions come up, please don't hesitate to email. I'll be happy to help out. When we come back next class, we'll finish off these notes here and then move into chapter 11 with the normal distributions.
Thank you.
Yep, have a great one. Thanks, Hayes. Have a good one. Thanks, you too. Try not to work too hard.